Okay, so good morning, bom dia, bem-vindos. So it's a great pleasure to welcome everyone here to this, the 8th edition, Geometry and Algebra, Algebra and Geometry. The first that I'm involved with, but I hope the first of many. And it's a special pleasure to introduce my friend and colleague from UFI, but now also coming to us from Università di Verona in Italy, Alessia Mandini, who's going to tell us everything that we're afraid to ask about polygons.
So thank you very much to the organizers for the invitation to be here. It is super nice, a big pleasure to come back to this conference and to Rio and see so many friends. So when they ask you a title for a mini course that you could give a year before the mini course will happen, you may feel inspired to make some joke and something. So someday, I don't know, I thought it was fun, this title, but then the day comes and you realize that this is actually probably a more realistic title for what you will have today, which is, if you think, I think I know about polygons, and hope you will like. It's an overview on a few things. The talk will be on the blackboard, but given the title, I thought I had to have at least one slide. So the plan of the talk is the following. I will, for the first part, I will really just talk of the moduli space of polygons in R3. So I will introduce, sorry, I was distracted. I will introduce it and describe a few of its properties, like wall crossing, maybe describe its cohomology, etc. And definition and properties, and then I will see relations. Maybe I can, and relations with other moduli spaces. And then, in the second part of the talk, I will still talk of polygons, because that's what I promised, but it will be in some different space, generalizing a bit the idea of polygons in R3, okay? So what are the very first part is really playing around with the polygons you learned at primary school, probably, but with a bit of a fancy language. So let's consider n positive numbers. So let alpha be a collection of n positive numbers, okay? And consider the two spheres of radius, the number associated, alpha I, okay? Just the two spheres in R3. This is famously a symplectic manifold equipped with the volume form omega I, right? And then so is the product of all such spheres that you chose, where you can equip it with a symplectic, in fact, Kähler form by just taking the sum of, you can even make it explicit. This is the sum of the pullback of each of the symplectic form, where the pi is from the product of the two spheres to the ith sphere, of course. Sorry for going on the other. Very good. So this is an Hamiltonian, this is a symplectic manifold on which we can consider the action of SO3, the group of rotations, diagonally. It's the diagonal action on the product of spheres. So we have n spheres, and we take the action of SO3 that rotates each of the spheres with the same angle, okay? This action is Hamiltonian. With moment map, it just takes the product of the sum of the alpha i's to, well, it goes to the dual of the Lie algebra of SO3, which I can identify with R3, of course. And what it does? Well, it takes n vectors, each of them lying in a sphere, and it sends them to their sum as vectors in R3. Okay? The moduli space I promised to introduce, moduli space of polygons, is nothing but the symplectic reduction that you can obtain with respect to this Hamiltonian action. So it's the symplectic reduction of the product of two spheres at the zero-level set. Okay, so topologically, you take the zero-level set for this moment map, and then you quotient by the SO3 action. Okay, so why do we call it the moduli space of polygons? Well, what does it mean to live in there? So an element, V1, let me write it like this, Vn, lives in this M alpha, if and only if, well, we need to have the following. We need to have that the vectors sits in the zero-level set, because I chose the zero level. So sitting in the zero-level set means that their sum is 0, which, if you think in R3, is just saying that you apply the first vector V1 here, and then the second, etc. You apply them consequently, and what you obtain is a closed piecewise linear path like this. Okay? Taking the quotient by SO3 just takes into account that if you have some polygon and you take a rigid motions of it, you are still in the same class. So you are really. A comment before going, what really matters in this construction is, in fact, the position of the vertices. So the polygons can do everything. Like they can self-intersect like this. You know, edges are allowed to self-intersect, or to come back at some point, and then, you know, like this, and then going again. And also, this is in R3, so we will have configurations like this, where, I mean, you should imagine it three-dimensional, okay? Very good. So there are a number of reasons to study this space, some of which I hope, are pure mathematical, and I hope I will make them clear also in the second part where I talk of the relations to other moduli spaces. But just to mention, to make a one-line comment, these spaces, they seem to have a real application, and I mean real. I mean, of course, there is an obvious application to robotics, because this can be an articulated arm. But there are studies that relate, for example, the symplectic volume of these spaces, etc., to some areas like this of protein foldings, etc., because, you know, the position of the vertices is related to. So, I mean, I'm totally not an expert. Actually, I know nothing about this direction toward applications, but I want to mention that they are there because I think it's a nice thing. Okay. So one more comment. So what is M alpha? Well, M alpha, so when smooth, M alpha is n minus 3-dimensional Kähler manifold. And when is it smooth? So the notion of being smooth is as a nice geometric interpretation. I mean, we are taking a very simple symplectic reduction. What can go wrong? It can happen that you have a configuration like this. Maybe I take these two colors. So if you have a few edges going in one direction, like Vi for I sitting in some index set I, okay? And some other of the edges that come back and stay on the same line, Vj for j in its complement. Then the aligned configuration like this in the level set, so if there is such a line configuration in the zero level set for the moment map, then in the quotient, this will produce a singularities because you can consider the S1 of rotations inside SO3, okay, that fixes this, and this will provide a singularity. So the notion of being smooth is the following. So how do I say? Well, not a definition, maybe. So consider the scalar quantity epsilon I alpha for the sum of the alpha I for I in the index set I minus the sum of the remaining ones. Okay? This you can consider for an index set I in 1 through n. So the thing is, M alpha is smooth if and only if the scalar quantity epsilon I of alpha is not 0 for every index set I. And in this case, I will call alpha generic, okay, if we are ruling out that condition. Very good. Oh, sorry. So there is, in fact, one thing that I just want to mention. Kapovic and Milson studied these spaces and the singular the quotient when you allow this singularity, and they proved that M alpha is in general a complex analytic space with at most, eventually, I mean, if it's not isolated singularity, and they can prove that these singularities corresponds to homogeneous quadratic cones.
So this is under the assumption that alpha is generic? I don't understand.
No, sorry. In general, so M alpha is a complex analytic space. If it's not generic, so in the eventuality that it's not generic, the singularities will be isolated and will be homogeneous cones. Otherwise, it's just a complex analytic space.
The whole of why you wrote alpha generic?
I mean, it was just in this case, so if so, alpha is said to be generic. So sometimes along the talk I will say, oh, let alpha be generic. What I mean is that this quantity is never 0 for every I. Yeah.
So you require n to be odd?
Sorry, didn't.
Are you requiring the n to be odd? The dimension
Not.
is n minus 3, so you're saying it's a complex analytic space.
This is a complex dimension.
Complex.
Complex dimension, yes. Thanks. Okay. Other questions? Okay. So these isolated singularities are homogeneous conus, quadratic cones. Okay. So I promised to play around a bit. So let's do the simple case of n. Let's do a few examples. So if we do n equal to 3, of course, it's very simple because we just have 3 length, and our polygon space is either a triangle of the prescribed length or the empty space, depending on the alpha you chose. So M alpha can be either the empty set or a point, depending if the alpha you chose satisfies or not the triangle inequalities. Okay? So the case n equals 3 is somewhat the simplest. The case n equals 4, I mean, let's see what can happen. So we will have 4 lengths. And so let's say I start with the first edge, V1, and then I attach the second V2 aligned. I may or may not be able, no, I will always be able to close like this. This, of course, corresponds in the moduli space to a point, because every twinkling that I can do to it is just a rigid motion, so it's a point. But if I don't put the V1 and the V2 aligned, then, but I fix the first 2 vectors, what I am in fact fixing is the diagonal among them. And then I have the V4 and V5, sorry, the V3 and V4. And to play around with. But what are the choices? The choices is, once I fix V1 and V2, hence this diagonal, are essentially rotations around this diagonal. It's where I put this V3 in the space. So this gives me an S1. And you can see that this goes along for all possible inclinations, so to say, that you can put in V1 and V2, or all possible diagonals D1, until you reach the other, so to say, special case where V3 and V4 are aligned, and this is again a point. So we will have later more machinery to understand the geometry of these spaces, but I still wanted to draw these pictures, because if you play around a little bit with this configuration, you can convince yourself that the moduli space for 4 gons is in fact, always we have the case the empty set, I mean in case it doesn't close, or an S2. I will go back to this. Of course, we have more machinery. This is a drawing intuition, nothing more than that. Yes?
In your definition of, or in your considerations about the smoothness, I think you have to assume that I has cardinality at least 2, right? Otherwise?
I has cardinality at least 2. Let me think a second. Because if I take cardinality 1, it will happen that the sum of 1s is equal to this.
These are the lengths, no. So
these are the lengths, yeah.
Yeah, I'm mixing everything up. So.
I mean, the cardinality 1 is there, and it has a special role. It will come in a second, yeah.
Alessia,
Yes.
on this particular case, for the same is S2.
Yes.
But there are singular points somehow. No, I mean, isn't there a way to see it as a start?
So I should have said it. I mean, there are for n equal 4, there are choices of alpha for which you have singular point. For example, the equilateral, right? Sure. Yes, I didn't want to consider it in this S2, and I mean, as you know, I never, so I believe it will be a teardrop in that case. Yeah.
So it's like,
Yeah, but this drop, yes. Well, not really a teardrop, you will have 2 of those, yeah.
you see that's S2 when you disregard
Yes.
the isotope.
Yeah.
But there is some bonds with the isotope.
Yeah, right. Yes?
But also you're claiming that this S2 concept canonically identified with CP1. And where is that coming from in this, for this 4 vector?
So, yes, I mean, Of course, these are not all the same S2 or CP1 because there is a Keller form coming from reduction that is changing, and I'm not describing it here. It depends linearly on the alpha you chose. And the relation, so why is this a P1? Taking a product of 4 sphere, doing the quotient. I'm not sure what, so what is, why do I get a P1 when n is 4? Or
It's a Taylor method.
It's what?
But I guess it's fine. You're looking at the symplectic structure from the
Yeah.
That's good.
Yeah. I mean, there is a rich geometry here that I am, in a way, not studying, that it would be interesting to, I mean, these are all Keylers, so there is Riemannian, there are things going on, yeah, and I'm not taking it into account, so there should be, there are more things. Okay. Another remark I wanted to make, due to Hausmann and Knudsen, is that this, of course, if you consider, so let Mn be the space of all n-gons modulo rigid motions, okay, so Mn can be equipped with a Poisson structure, so it's a Poisson manifold. Of which our M alpha are the symplectic leaves. So these M alpha fit together as a foliation when you don't require to fix the alpha. Okay? Very good. The symplectic leaves. Okay. More questions, comments? So if not, I will take a slightly broader point of view.
Just
Yes.
question, sorry, Alessia.
No problem.
This Poisson manifold is the same as the product of the spheres modeled out by the action of the sphere. Is this?
No, because to have the sphere, you need to fix the alpha,
Okay.
right? I believe, even from what will come, I haven't checked, but I believe that it should be the quotient of C2n with its canonic, with some, it should be a +1 quotient, but from C2n, because the choice of the alpha already fixes
And
the
why not the product of the R3?
Maybe it works like that as well. The product of the R3? I have the help from the audience as well.
When you fix it as a lens, you will take a fiber.
Yeah. Okay, product of the R3. Thank you. Okay. Polygons as quiver varieties. Okay, so this is a bit broader point of view that will be helpful in many points of the talk. So a quiver is, to me, is just a collection of vertices and arrows between some of the vertices. And I will make a specific choice of a quiver, which is the so-called star-shaped quiver, where I take n+1 vertices, And each of them have an arrow pointing inwards. Okay? Then to construct the Keller space associated to this quiver, I should choose the dimensional vector, which I do. I choose 2 and the sequence of 1s, which means, in a way, to me, choosing vector spaces for the vertices. So I choose a C2 for the inner vertex and a copy of C for each of the outer vertices, right? So the representation of this quiver is just homomorphisms between the vector spaces I chose whenever I have an arrow connecting the vertices. So it's a homomorphism from C2 to C, and I have n copies of them. Okay, so this is just another way of writing C to n. Yes?
Sorry, the central vertex is C2?
Yes.
And so the homs go in the opposite direction to the arrows? Or?
The I've written it wrong. Thank you. Yes. Thank you. From C to C2, yes. And in fact, what I wanted to say is that in here, I choose coordinate Qi, where each of the Qi is a column matrix from C to C2, right? Okay. So what I do now, following what I think is Nakajima recipe, you consider the group that is associated to the vector spaces you chose. So we have U2 for C2. You have the torus of diagonal matrices in UN for each of the copies of C. And then I want to quotient by the diagonal circle in this product for the action diagonal S1, right? Because the action will be by conjugation. Then, this is a bit. Okay. Then the action of K on C2n by conjugation, I mean, I can even write it out, is I never get. So if you choose an element A, lambda 1, lambda n in K, and you act on C2n, so you have Q1, Qn, and the action is given by each Qi is taken to A minus 1 Qi lambda I, action by conjugation, okay? This action that I've written here is a Hamiltonian, and as such, as a moment map that goes to the dual of the Lie algebra of K. And this moment map is just taking coordinates Q1 to Qn. Then we have a component that will be in the dual of the Lie algebra of U2 or SU2, and that will be the sum of the Qi star traceless part. The traceless transpose conjugate, okay, so this is 2x2 matrix, and this sum really sits in the Lie algebra of SU2. And then for the components in R, you will just take 1/2 the norm of the Qi squared. Okay? So the claim, the theorem that, I will try to use the other. The theorem that you can find in Hausmann and Knudson. They don't use the quiver description, but I think the idea is there. Hausmann, Knudson. Is that the symplectic quotient of C2n by the action of K with respect to 0 alpha is exactly the polygon space M alpha that I had described before, okay? And the idea of the proof is, in fact, very simple and very constructive, because what you do is you just identify R3 with the dual of the Lie algebra SU2. You take an identification, right? And then what you say is that a vector Vi in R3 corresponds to the matrix Qi star traceless part. Okay. Actually, I could set inequality here. So if you do so, the fact that you chose 0 for the first component of the moment map, it gives you the closing condition of the polygon. So this traceless part implies the closing condition. While the other moment map conditions, these ones, so the norm of the Qi squared equal to alpha I, impose the length of the vector Vi. I may be off by a factor, I realize now, but I mean, it's everything adjustable. Okay, so the correspondence is very explicit. And this description, it's really, I like it very much for a number of reasons. One of which is that it shows a rich geometry of these polygon spaces, because you see we are now realizing them as a quotient of C2n by k. So from C2n, if we perform a symplectic reduction by k, I'm claiming that we arrive to M alpha. But we can perform this symplectic reduction by stages. Okay, the product is a group. Nobody prevents us from doing it by stages. So if we first quotient by the product of the U1n at the alpha level set, what we obtain is the product of P1s that I will again write as 2, if you allow me. And we recover the starting point of before, a product of spheres of radius alpha I. And then we are left with the residual action of U2 mod out by the diagonal circle, which we can write as SO3, modulo some identification, and we obtain the polygon space. So really, so the previous description was just a zoom in this part of the picture. But of course, you can also perform the reduction in stages in the other order. So if you first perform the reduction in stages by the group U2, what you obtain is the Grassmannian of 2 planes in Cn, okay? On which we have the residual action of the group U1n, and when you perform this quotient at the alpha level set, Hausmann and Knudson tell us that we obtain the moduli space M alpha, okay? So the construction is really nice and carries quite a few consequences. For example, we will see, well, one will come in a moment, and the other, you see, the length vector alpha that I chose at the very beginning appears now as a level set for a moment map. So we have this moment map for U1n from the Grassmannian Cn to Rn. And then we have here some set of admissible alphas, okay? So this image of the Grassmannian via this moment map has, of course, a division. I mean, the drawing will be of course, not good because I can't draw in Rn. But it will have a division in chambers and walls. And which is, I mean, in a way, it's already on the pictures, because what are the walls? Well, the walls, they are in correspondence to index set I, so they are a collection of alphas, of positive alphas, such that epsilon I of alpha is 0. And for every index set I in 1 through n, we will have a wall. I mean, of course, a wall is equally identified with by choosing I or its complement, obviously. Okay? So these are the walls, and it is interesting to study what happens when you cross such a wall. So how does the moduli space of polygons change when you go from a chamber to another? I mean, of course, this is, can be stated in bigger generality, and one expects that there is a birational transformation. But what I want to say is that this birational transformation, which is the composite of a blow-up followed by a blow-down, in this setup as a nice polygon description, which is the following. So, wall crossing. Okay, I'm going until 11, right? 9:30, okay, good. So, what will happen is the following. Assume we choose a wall, Wi, which we know as this equation, and hence we have a point alpha plus and another alpha minus on either side of the wall. So on this side, we have that epsilon, well, I will write it down here. Epsilon I of alpha plus is positive, which means that the sum of the alpha I plus for I in I is bigger than the others. Okay? And for the other, of course, we will have the other way around. And if we want to cross a wall, we may also want to consider a critical level where epsilon I of alpha critical is 0. Okay. Can I erase this division? Is it important for recording issues? Maybe not. Okay, so what will happen is that in alpha plus, we have these conditions, which means that there is actually implies that there is a relevant submanifold in M alpha plus, which is the following. It's so M alpha plus IC, okay? So if we define it formally, this is the collection of those polygons, M alpha, such that the Vi are proportional, positive proportional to Vj for every I and j in the index set I. So if I said, okay, this is an IC, perfect, with lambda a positive number, okay? But of course you can define it by drawing, which I like a lot, by saying that these are all the polygons for which you have the vectors V, sorry, this doesn't look very aligned, the vectors Vj for j in I complement aligned, and the others, these are the Vi for I in I complement. right? And this is a submanifold of the M alpha plus. And of course, because of this other inequality in M alpha minus, we will have the twin submanifold, which is obtained inside M alpha minus by considering the, sorry, this is an I. Okay. By considering that the vectors in I, Vi for I in the index set I, are all aligned. Okay? So these are the two submanifolds that are involved in the wall crossing. Where did I put? So the diagram that I like to draw is the following. So we want to go from M alpha plus to M alpha minus. And of course, in between, we have a critical situation, M alpha C. So in M alpha C, we have a line configuration because being critical, it means that if we put the Vj, Vi's for I in I all aligned, we can still come back with the Vj's. Right? And I've said that in these two manifolds, we have these relevant submanifolds. Now in here, we are putting the IC, so it will be like this and this, whatever, something like this submanifold, and this other submanifold here, formed by these, okay? So what happens is that you can blow up M alpha C at the singular point, so you will have M tilde, which is the blow up at the singular point, which will contain an exceptional divisor, right? And this exceptional divisor is precisely the product of these two submanifolds. And this is, I mean, how can I, yeah. It's exactly the product of Mi times MIC. Okay? So what happens when you have these two small resolutions of the singularity here, and what happens when you cross a wall is that you have this relevant submanifold. When you approach the wall, these polygons kind of get thinner, thinner, thinner. They are aligned on the wall point, and then you are inflating in the other directions a little bit. Okay? So it is a very explicit description, and being a mini course, I have a number of examples. For example, let's consider the chamber. So to give you a chamber in this moment image, for example, it's enough to give you a collection of short sets, right? To identify a chamber, I tell you which are the sets that are shorts for the alphas. Oh, sorry, I didn't say what short mean. Yes?
Also, alpha C is generic in the wall, because if it is in the intersection of two walls.
Yes, yes, I want it to be generic in the wall, yeah. Yeah, right. But yes, I haven't said what being short and long means. Sorry, sometimes. So let me do here a comment. Definition, alpha in R and plus is, sorry, So let alpha be some length vector. So an index set I in 1 through m is short if and only if epsilon I of alpha is negative or alpha short. And it's long otherwise, of course. So very intuitive. Okay? So to identify a chamber in this moment polytope, it's enough to say which are the short sets for the alphas in this chamber. Okay? Very good. So let's define a chamber delta 0 by saying that its short sets are the following. So all the singletons except for I different from 3, and then I want to take jk for j and k that can vary among 1, 2, 4, and 5, and then ijk for I, j, and k also varying from in 1, 2, 4, 5. And then I want the set 1, 2, 4, 5. Okay, let's say I choose alpha in this delta 0. What is the corresponding polygon space? As a mini course, I have exercises for you. Take a second to think about it. It's a collection of short sets. And it's a partition, so the others, the complements, will be long. What?
In order for that picture to hold, shouldn't the elements of I be contiguous elements? Like they should be consecutive numbers, right?
The elements of I, this index set.
The subset needs to be, the elements of the subset need to be consecutive numbers, right?
Yes, in my drawing, I've put them in a line like this because I think it's more visual. But the definition is really this. They need to be proportional. But this, I take the opportunity. So no, in a way, the drawing is a bit misleading. They don't need to be consequent. This is a definition. I like it to draw like that. But let me take the occasion of your clever remark, thank you, to make 2 comments. So if you alpha, I can say alpha generic, but it doesn't matter, is whatever the equivalency is symplectomorphic or a complex analytic space to M sigma alpha, where sigma is a permutation on the order. So they are order, but if you change the order, it doesn't change the structure, okay, where sigma is a permutation on the order of the edges. So this is why, to simplify, I draw it like this. I reorder in such a way that they are consequent, and then I see a long straight. So this is the first comment. And the other is that M alpha is conformally symplectomorphic to M lambda alpha for every lambda positive. Conformally symplectomorphic, it means that we are just rescaling the symplectic structure, okay? So they are not symplectomorphic in the sense that the lambda factor changes the symplectic structure, but I mean, other than that. So this is one comment. And the other comment that I forgot to make, but your question made me remind, just give me a second, is that there is a reason why I wanted to draw it like this. It's because I wanted to comment that this, in fact, this manifold, it's of course a moduli space of polygons itself. This is the moduli space of polygons where I choose one, so I choose length is alpha I for I in I, and then I have a long length, so let me write it better, otherwise it's really not clear. So this is a polygon space itself, alpha tilde, where alpha tilde is just the alpha i's for I in I. So alpha I1, alpha ik. If I say that my I is I1, ik. And then the sum of the other ones, the sum of the alpha j for j in the complement. Okay? So this is what I had in mind when I was saying that the submanifold involved in the birational map of the wall crossing are polygons themselves. They are, in fact, polygons of lower dimension. They have one long edge, which is the sum of the alpha i's for I in the complement, which I draw a line. And then the others are what they were before. So thank you. It clarified a bit. And also, it gave you some time for the exercise. So what is this M alpha?
Isn't it empty?
It's empty. Very good, Matthias. It's empty because we have a long set. So because, notice that 1, 2, 4, 5 being long, being short implies that the index set 3 is short. Sorry, is long. I'm saying it all the way. Okay. But having a long edge of cardinality 1 implies that the closing condition can be satisfied. Where did I put the eraser? The one I like here. Yes, because so having this 3 long, we have a long edge, and there's no hope for the others to come and close the polygon. So this is the empty set, and this will happen every time that you have an index set of cardinality 1 that is non-short. So this also characterizes the external walls that appear in here, because these are walls Wi for some index I of cardinality 1. These are the outer walls. Okay? When you cross, you go out, and the alpha is no longer admissible, or I mean, the associated polygon space is empty. Okay. Very good. So so let's cross a wall. We were outside. We go in. Crossing a wall means that we can consider delta 1, where essentially everything is the same, except that I now include all the I are short, and then I have J and K, same things. Sorry, this is 1, 2, 4, 5. And then we have, what do I have? IJK. Okay. Okay, fine. So we cross the wall. This is, this delta 1 is non-empty. For example, we can find an index set. I will keep the one I have in the paper, even though it looks a bit awkward. I mean, you may wonder why 1/7. It's not forbidden, and it's only because, these are, as you see, because of this comment that M alpha is conformally simply ectomorphic to M lambda alpha, these are cones in alpha. So you can slice in some way, for example, fixing the perimeter, and then you obtain chambers. So this 1/7 comes because of the convention I made there to fix the perimeter. So this one, you can check, sits in delta 1. So this chamber is non-empty. And also it is easy to see that we obtained it by crossing the wall W3, right? So what happened according to our wall crossing condition? Well, we started from the empty set. We approached the wall. And on the wall, we had a lined configuration where we had the index set in here. So I have conveniently this as a wall. So in here, we have a lined configuration with a long set, V3, and all the others come back. Right? And then we blow up this point. If you blow up this point, you get a projective space of the appropriate dimension. So this M alpha is the projective space of dimension n minus 3 for every alpha in delta 1. Okay? And this is true for every external chamber, where an external chamber is a chamber whose closure contains an external wall. The associated polygon space is a projective space of the expected dimension, right? Very good. Of course, what changes with the alpha is the Keller form that you equip on this projective space. Okay, so this, I want to use this to make another comment, because this allows me to say that this relevant submanifold MIC and its twin MI are in fact projective spaces. Why? Because MIC alpha plus, you see, is simply ectomorphic, in fact, to this M alpha tilde, where we have a long set. This, because of the condition, is our long set. So this here is a projective space of dimension cardinality of I plus 1 minus 3 give me a minus 2. And this here is a projective space of cardinality of IC plus 1 minus 3 gives me a minus 2. Think about it, okay? So this exceptional divisor is in fact, we identified this two submanifold as a product of projective spaces of the appropriate dimensions. Okay? Questions, comments? So, as promised, I have a set of exercises for you that will come handy later, so we'll write them. So let's cross another wall. Let's choose another collection. We have the short sets I for all I, and then we have JK, same as before, I won't rewrite. And then we have 1 JK for every J and K that varies through 2, 4, and 5. Okay? So which wall did I cross? Trying to keep you awake at this time of the morning. If I'm not mistaken, I changed the 2, 4, 5 short set, right, for the, sorry, this isn't complete. And I should put here 1, 3. So because here we have that the J and K were going from 1, 2, 4, 5. So the wall I crossed is 1, 3. You can have fun and do the computation. You will see that this amount to blowing up a point in M alpha corresponding to delta 1 and obtaining a projective space of dimension 1 on this side. These two examples will come handy again later. Again, this is not empty, and for the sake, because of what will come, I will also put another example. Okay, very good. So I believe this is, for the time being, what I wanted to say about the wall crossing. Okay. Good. Actually, I have another exercise for you, which is compute. I mean, with this wall crossing, essentially what you get is the diffeo type, right? I'm not describing the Keller structure. But you could compute what is the diffeo type of the equilateral case, let's say, for n equal to for 5 and 7, whatever. The even one, of course, are not smooth. I mean, it's these equilateral cases have themselves they are interesting by themselves. They are, for example, for those who knows what this means, the only of these polygons that are monotone. So they're interesting cases, but I won't get into that. Okay. Good. So what I want to say now is that when I was studying this wall crossing description, I had an objective, which was to find a set of generators for these polygon spaces. And in fact, so I erased that, but I can rewrite. So remember, there was, in this part of the blackboard, we have that we had this essentially, so we were going from the u1 n minus 1 alpha inside the Grassmannian of two planes in Cn. We were taking the quotient to our polygon space M alpha. Okay? But this quotient is by this torus. Of course, you can take also this reduction in stages. So for example, you could quotient by n minus, for the first n minus 1 S1s, and just keep the last. And this will give you so you can take so let Ci be the first Chern classes associated to this. Maybe I can. So I want to take. So it's clear what I want to do. I think I want to take the quotient first for to isolate an S1 per time, and then consider the first Chern class of that vibration. right? And this associated to the NS1 bundles. Above, I mean. This is a bit sketchy, but I hope it's understandable by taking reduction in stages. I mean, it's nothing complicated. It's just I don't want to go into putting the indices. Okay. So it was proven, I later figured out in Hausmann and Knudson, and I reproved it later using this wall crossing analysis that these CI generate the cohomology of the polygon space. Okay? So essentially you have one of these for each edge. And because of the wall crossing analysis, what happens when you cross a wall is that, how do I say? Well, let me state the theorem and then do the example, and hopefully it will be clear. So there is a result due to Guillemin and Stenberg. That tells you that if you have a set of generators of the cohomology, so if so in this setup, we have that the cohomology of the manifold is just the C of, let's call the generator x1 through xn, because I think of that, quotient by the annihilator of the volume of the polygon MR. Okay, what does it mean? It means that an element is in the annihilator. I will write it now. If, so an element, polynomial Q x1 through xn belongs to this annihilator, if and only if, when you apply it to the partial derivatives with respect to the alpha i's, this is it. So as you see, everything is very combinatorial. And we are lucky enough because there is an explicit formula for the volume of these polygon spaces that was computed by a number of people. Maybe the first two were Takakura and Wutekoi in separate works. And the formula says that the volume of MR, oh, sorry, it's the alpha. Yes, yes. Sorry, I have a confusion in my mind because when I studied the polygons, at some point I switched from R to alpha. because I wanted to keep the R free for the rank of some bundle. And then I have this, sometimes R is alpha, sorry. Okay. So the volume of M alpha is a beautiful volume formula that starts with a minus, but I guarantee you it's positive. And then we have 2p n minus 3 over n minus 3 factorial, and then we have this sum. Do we have something more here? Yes. Minus 1 to n minus the cardinality of I, epsilon I of alpha for I a long set. Whatever. There are several ways to prove this theorem, for example, by localization formula, etc. I decided not to go into it. Anyway, it's very explicit, very combinatorial, and polynomial in the length. I mean, this is some sums, etc. And maybe I've forgotten. You know, I never computed it. So this is an homework for me for Wednesday. Thank you. I don't know if it will. I will just plug it in some. Yeah. I'm not sure what we'll give. So what happens is that you can just do it yourself, or say your computer to write down the volume for some choices of this alpha, or some sets, and determine the cohomology. So, for example, yes.
About the definition there. If and only if the partial derivatives are taken with respect to alpha or with respect to x, I cannot see. Is it alpha I, right?
Yes. So I replace. So I say that it's my set of polynomials, but then, so this is a polynomial in the xi, and I essentially compute it in the position of the xi. I put the partial derivative with respect to alpha I. Yeah, there is a bit of swinging of the notation here. Okay, so if we do, for example, so you see, I had prepared the examples, but I skipped the empty one. I will. But if we take the delta 1, so alpha, let me put numbers so I can refer to them. If we do alpha 1 in here, yeah, and alpha 2 in here, so I will not. Actually, sorry, I don't want to be the specific one. I want to be just, because otherwise, I mean, you get a number, not a function. I want alpha 1 to be in delta 1. Then you obtain that your volume for this m alpha 1 is 2 pi squared 1 minus 2 alpha 3 square. In this simplification, I'm using, again, the fact that I fixed the perimeter, so I sliced. And this is why. Okay? So you can nicely compute what are the polynomials that sits in the annihilator, and you obtain that your cohomology for the polygon space is exactly C. Yeah, sorry, I have, here I want really to write this. I want to call it C3, because, I mean, I could call it X or whatever, but it's really the first Chern class associated to the third edge in this vibration, okay? So if you allow me, sorry for messing up the notation along the talk, maybe. What?
Because sometimes C3 is a third Chern class, but this is a first Chern class.
It's the first Chern class. That's why I wanted to write it in words, because these are all, these are all first-term classes. Yeah. Yes. As it's good to get when your space is a projective space. We are all happy. And then, if you do for the after crossing the wall, I mean, what you would expect is that you gain a class for the exceptional divisor, right? Which is exactly what happens. So if you take alpha 2 in delta 2, you can check that the volume of alpha 2 is 4 pi squared 1 minus alpha 1 minus 2 alpha 3. And then you compute that, where did I put it? That the cohomology of your M alpha 2 is exactly, sorry, it's C of C1, C3 with C1 cube and C3 to the third. If you really want to see the exceptional divisor, you make a change of basis to minus C1 plus C3, and you really see the self-intersection. Yeah, and sorry, it's probably a square in both. C1 times C1 plus C3. I have a bit of confused notes. Let me fix this exercise. Sorry. Yeah. Yes, I always say in class, sometimes I put in some mistakes for you to be awake.
When you cross the wall, since these are zero-dimensional schemes, when you cross the wall, the degree is the same, but because here it's not the same, but let's say here makes sense.
Yes.
We expect to find the same degree after we cross the wall, because we have a turbinian of degree 3 for 1.
What you expect to see is to appear the Chern, to appear the exceptional divisor. So in here, for example, you expect to see the C1 appearing because you have this 1, 3 appearing that amounts for the exceptional divisor. The degree, I'm not sure, yeah. I'm almost done time-wise. Aye. Okay, so I will leave a few things for Wednesday. And I want, in particular, the relations to other spaces, such as representation and parabolic bundles will come on Wednesday. But I want to mention that this computation of the wall crossing has been, I want to mention I will finish with my favorite line, which is, these polygons can be generalized in a number of ways because, I took polygons in R3. You can see the edges as being geodesic in R3 with symmetric. You can see it in many ways, but the way I like it best, it's what I sometimes call the polygon game, which is the following. You just take your favorite Lie group and you consider, you denote by G star the dual of its Lie algebra. And then what you are doing, so you can consider a bunch of coadjoint orbits, coadjoint orbits of G that sits, of course, in G star. And these are symplectic manifold equipped with the constant Kirillov-Seriaux form. Okay? So is the product of such coadjoint orbits. Okay? Maybe I can write it symplectic with KKS symplectic form. So the product is also a symplectic manifold on which your group G acts diagonally by coadjoint action on each of the coadjoint orbits. And the moment map for each of the coadjoint orbit is just the inclusion in G star, and because we take the product, if we do n such thing, their moment map will be the sum, as in G star. Okay? And then, if you want, you can study the quotient of this product of coadjoint orbit by the action of the group at the zero level set. So if you do it for the group G equal to SU2, you obtain the polygons in R3 because you identify the Lie algebra of SU2 with R3. And it's all that I described today is about this one space. But of course, you can do it for any other group. In particular, a student of Leonor Godinho and Carlos Florentino has done it, the wall crossing for SUM. So at this moment, you can write the PhD thesis of Carlos Sotillo, which is online at the webpage of the University of Lisbon. And they are writing the paper along with Carlos Florentino and Leonor Godinho that were supervising him. The paper is not yet available. So what they do is they generalize the wall crossing for SUM, okay, but considering not all coadjoint orbits, but the degenerate one, so the projective spaces. In terms of quivers, considering in terms of quivers, what they do is the same picture, the same star-shaped quiver, but choosing dimensional vector m, sorry, maybe I'll do it 0, 1, n, and what they do is V0 is Cm instead of the C2, and Vi is C. And you perform all the machinery I told you. You obtain that the partial, it can be described also as a quotient of the Grassmannian of M planes in Cn. And you study the wall crossing, which of course get combinatorially more complicated, but nicely enough, they recovered that the birational map that relates the wall crossing is still a composition of a blow-up followed by a blow-down where the involved submanifolds are polygon spaces themselves. As far as I know, there is no volume formula in this case or cohomology description. And also, I mean, one could generalize much more by considering generic SUM coadjoint orbits, so eventually not complete flags or flags, full flags. So there are a few lines in which this work is being generalized. Thank you very much.